Last video I went from basic mathematics through quantum mechanics up to electron orbitals, and as such I will not be repeating myself, so with electron orbitals is where we'll start. So, 1s orbital looks like this. Now let's say that we take two 1s orbitals and we bring them closer together. Due to the rules I've explained in the last video, when you bring them closer together, these two orbitals become two new orbitals, the bonding sigma and the anti-bonding sigma. As the name would suggest, the bonding sigma helps our molecule bond, whilst the anti-bonding does the exact opposite. And whilst in the last video we've talked about this through a lens of quantum mechanics and wave functions, this time we'll focus on the orbitals and shapes. So, sigma bonds look like this. Anti-bonding sigma looks like this. Now you can see that the bonding brings the atoms together, whilst the anti-bonding pushes them apart. But the bond between two hydrogens I've covered before, so let's focus on some new material. For example, a bond between two p orbitals. Whilst s orbitals are simple spheres, p orbitals are hourglass shaped, so a bond between them will look more like this. And this is a pi bond. So I feel like the difference between a pi bond and a sigma bond is pretty clear and pretty self-explanatory, but what's important to see is their energy levels. So basically, when we have a sigma bond, the bonding sigma is lower in energy than the s orbitals, whilst the anti-bonding sigma is higher. Now, do keep in mind that less energy means more stable bond, because everything in our universe wants to have as little energy as possible. This means that if we start with one electron on each s orbital, both of them will fall onto the sigma bond, reducing energy, causing it to be more stable. But if we start with two each, two will go to sigma, two of them will go to anti-sigma, and you need more energy, no bond. That's why hydrogen bonds and helium doesn't. Now let's add the p orbitals to the picture like so. There we go. We've got additional 2 orbitals per subshell, which means that we've got 3 orbitals per side. This is what they all look like, and as you can see, p means this kind of hourglass shape, we'll get to it soon, and each of these orbitals is just a different orientation. Now when they bond, they produce 2 pi bonds and a single sigma bond. And we've already got a couple of things to discuss. First of all, pi bonds have a smaller difference in energy than sigma bonds. This makes them weaker and... okay, think about it this way. Imagine that you have a weight on a table. Heck, imagine you have 2 weights on a table. One heavy and one lighter. Here on the side, I'll add these bars to represent potential energy of the weights. They both start at the same point because potential energy is relative, and we have 2 additional states we can reach. First, we can drop the weights, which will reduce the potential energies, and since the more massive weight has... let me just... more mass, it will drop more in energy. The lighter weight will drop less in energy. Then the next state we need to concern ourselves with is what happens when we bring the weights even higher. Once we do that, the energy of the heavy weights increases even more than the lightweight, simple as it could be. Now what this effectively means is that if you drop both our weights, then the heavier weight will lose more energy, and therefore it will be even more stable, because you'll need more energy to bring it up. The same way it works for our bonds. The sigma bond is a kind of like our more massive weight, the pi bond is kind of like the lighter, hence why the drop and raise in energy is greater here and smaller here. So this is kind of like our weight hovering in space, this is kind of like the weight on the table, and this is kind of like the weight on the floor. So there, that's how the s bond can be more stable. Now next, how can p orbitals form pi bonds and a sigma bond? Well, the nice thing about this video is that we've done all the heavy quantum lifting in the last one, which means that instead of having to explain it with mathematics, I can just show you that this is our first pi bond, this is the second, and then this is the sigma. It's really simple when you put it that way, isn't it? So now, if we go on and display all of the orbitals of nitrogen, once again, with this axis representing energy, in this case these arrows will represent electrons again. Up arrow for electrons with up spin, down arrow for electrons with down spin, it doesn't really matter, the point is each orbital can hold at most 2 electrons. And if I bring in another nitrogen to the mix, then the bottom s1 orbitals will come together and creating a bonding sigma and anti-bonding sigma. The two s orbitals will come together and create a bonding sigma and an anti-bonding sigma. And then the two orbitals that are head-on will create bonding sigma and an anti-bonding sigma, whilst the other two create bonding and anti-bonding pi. Now we have all of those orbitals, but not all of them are filled. So in order to figure out which ones get filled, we take our electrons and we start filling them, bottom to top. And there we go. This is the bond structure in nitrogen gas. Now I will zoom in on all of these bonds and slowly go over all of them, because there is a lot of information and I want you to understand it. First, the nucleus with 7 protons and 7 neutrons. Protons all have positive charge, so they push themselves apart. Neutrons don't have a charge, so using a spillover strong interaction, the nuclear force, they keep the nucleus together. Then this positive charge attracts negative charges. And what has negative charges? Electrons. So it attracts 7 electrons to balance itself out. Then these electrons have different shapes. So first we start with the two 1s orbitals, then two 2s orbitals, then 3 2p orbitals. And there, behold, a nitrogen. Now as we take another nitrogen and bring them both together, the electrons change. And now they look like this. We have 2 electrons on the 1 sigma orbital, 2 on the 1 antibonding sigma, 2 on the 2 bonding sigma, 2 on the 2 antibonding sigma, and then 2 on the sigma bonding from the p orbitals, and finally 4 on the 2 pi bonds, and there, we've run out of electrons. So this is what those orbitals are, these shapes. So why did I show you them from the perspective of energy? Well, it's because if I take the differences in energy between nitrogens on their own and in a bond, then this is what we get. We have to remember to duplicate the nitrogens on their own because that's 2 of them, and then if I just put all of these cylinders together, we get more energy from nitrogens on their own rather than in the bond. Which means that if you want to break the bond, you need to make up the difference in energy. So this is the energy you need to put in order to break the bond. Or in other words, this is how much energy nitrogen emits when it goes from atoms to a molecule. Or conversely, how much energy you need to give it to break the bond between nitrogen atoms in nitrogen gas. And so there we go. This is what the bonds look like, this is why they happen, this is why molecules don't randomly break down. And oh my goodness, we just started the video. Okay, that's because our orbitals don't need to go into a bond to change. They can also hybridize, a topic I've briefly touched upon in the last video, but this time, to give you a more concrete understanding of it, imagine a carbon atom. In this carbon atom on the valence shell, which just means the outermost shell, we have 2 electrons on the 2s and 2 electrons on the 2p. Now you might be wondering, which of the 2 orientations the electrons are on, but well, they are on all of them, but only on the 2, if that makes sense, which it shouldn't because it doesn't make sense. So basically, let's just say that the universe doesn't exactly know where they are until we do something with them. So with that in mind, let's imagine we bring in our 4 hydrogens to our carbon. It does have 4 free electrons ready to bond, so it should be fine, right? Well, yeah, but if we were to bond them right now, then 2 hydrogens would have to bond with the p orbitals, and the other 2 would have to bond with the s. Well, it's because electrons all have negative charge, and same charges repel, so they all want to stay as far away from each other as possible. So that's why they move to the opposite side, except if that's the case, then which hydrogens would go here and which hydrogens would go there? Well, remember how with the p orbitals, if you have 2 electrons out of 3 orbitals, then they won't occupy any specific 2, only they will occupy some 2 of the 3. This follows a wider trend in chemistry, where if there are certain identical objects and certain states they can occupy, then they don't really want them to be mismatched. Basically, since all hydrogen atoms are identical in this case, there is no reason for some of them to have a stronger bond than the others. So what happens? Well, what happens is our 4 orbitals get together and hybridize. From 1 2s orbital and 3 2p's orbital into the sp3. Which looks like this, with these being the orbitals, and as such you can see that in methane, all of the hydrogens move as far away from each other as possible. bringing their electron clouds with them, like so. But sp3 is not the only one. You can also have sp2, which would look like this. And in this case, in carbon, we're combining the s and p orbitals to create a three-legged orbital, like so. Now, where would that be useful? Well, for example, in benzene, where the atoms look more like this. So each carbon is bonded to a hydrogen, and next to carbons, like so. And here's the entire molecule. Except those are the two s orbital electrons and one p orbital electron taken care of. What about the last p? Well, that one didn't hybridize, and as such we still have all of them available. So what they do is they just merge together, like this, and form a ring. And this ring is actually what makes benzene so unique, and it's actually bound by all of these bonds at the same time. And as a small tangent, if you've ever wondered if benzene has double bonds or doesn't, well, these are the bonds. It's useful sometimes to think of them as double bonds that are constantly shifting, but that's just like a model, an approximation, and this is the actual bond. And so by now, I hope you can look at this graph and understand what's going on with each of these bonding orbitals just being a different combination of the underlying atomic orbitals, either interfering constructively or destructively. And that's how we get bonding and anti-bonding orbitals. You can think about it this way. When you have two waves, you can either combine them constructively or destructively. And due to reasons mentioned in the last video, orbitals are waves, so they can either combine constructively to make a more bonding orbital, or destructively to create a less bonding orbital. And in benzene's case, since we have so many orbitals combining together, we get a lot of combinations. So these are possible orbitals. And so that's all the detail about bonds that I'm going to get into for now, or rather typical covalent bonds, because next we have the metallic bonds, and oh my, this is gonna be a fun one. So first things first, so far we've talked only about the atoms from the first three periods of the periodic table, but as you go further and further down the line, the rules change. I mean, okay, they don't change, the rules obviously don't change, it's physics, but for chemistry we have the quantum mechanical rules, and then we have like simplified general rules, and as atoms get larger and larger, the general rules become less and less accurate. And so with that context, let's go to metals. The number one theme of metals will be their delocalization. So basically, in something like lithium, for example, when it bonds to form dilithium, it creates a simple sigma bond. This bond has a specific shape, specific location, specific rules. However, when you're dealing with larger atoms, then these orbitals can come together, and instead of forming just a simple bond between two atoms, they all come together and all play a part in this bond, leading to effectively a huge mess. Imagine benzene, but instead of a donut, it's just a vague blob. Now each time we add an additional atom to the mixture, we get more and more energy levels. So we start with something kind of reasonable, like let's say a 5 for a single atom. Now if we bring another atom, then we get like 10 orbitals. And if we bring in yet another, we get 15. And then so on, so forth, and each time we get more possible energy levels our electrons can occupy. And the crucial thing here is that this doesn't actually have a limit. So if we disregard the exact figures and just focus on the ballpark, we start with only one energy level, then a couple more, and so on, so forth. So we can keep adding and adding and adding these energy levels until we get a lot of them. Like a real lot of them. And then, there we go. That's metallic bonding. So why do we differentiate between them? Why do we think of a metallic bond as separate to covalent? Aren't they just the same thing, with covalent just being smaller? Well, yeah, fine, I guess you could think of it that way, but there's a reason to the madness, and that is, as always, energy. So basically, imagine that you have a bond between two oxygens. In this case, we disregard all of the underlying s orbitals because they just cancel each other out, and we just get to the sigma bonding orbital, the two pi bonding orbitals, and the half-filled anti-bonding pi. In that case, we first start filling them into our anti-bonding pi, and then in order to add even more, we need to jump this gap, and that is a pretty big gap. Next, let's look at benzene. In benzene, we have these aforementioned multiple possible orbitals. This gives us more freedom because the gaps are smaller and there are more possible states for these electrons to take up. Then, let's look at the metallic bond. Depending on how many ions we add, we can get a lot of possible orbitals. This is what defines metallic bonding and attributes it with the best properties. But first, it's really crucial that you understand this principle. So here's how you can think about it. Imagine that you are a ball, and in front of you there are some stairs. These steps represent the possible energy states, the orbitals, the shapes from before. Now for simple molecules like oxygen, they would look like this. For more complex molecules like benzene, they would look more like this. And then finally, for metallic bonds, since we can add as many atoms as we want, we can just keep on increasing the amount of steps. Forever, until our stairs become a ramp. For you as a ball, it's much easier to scale a ramp than it is to scale steps, so you can pass much easier through a metallic bond than any other. And that is why metals are conductive. What makes metal atoms metallic is the fact that they form metallic bonds. What makes those bonds conductive is precisely this property. So here's where we get to a brief introduction to conductivity. Okay, from now on I'll represent our metallic bond with a structure like this. In this case, the height, as always, represents the energy. The width of the thing represents how many electrons the energy state can house, and you can think of it as like our orbitals from before. In our nitrogen molecule, this level of energy can house 2, because it has only 1 orbital, but this energy level can house 4, because it has 2 orbitals. And the reason why you can think of it like the orbitals from before is because, well, these are orbitals. There are just so many of them that it would be pointless for me to even try to represent them. So yeah, each one of these lines is just a bunch of different shapes that our electrons can take, and the higher up you go, the more energy these shapes require. Then we'll have a line like this. This line represents how many of these orbitals are already filled with electrons. So, why is that useful? Well, it's because with this kind of representation, we can already understand bands, gaps, conductors and insulators. So basically, and very briefly, because I want to make a separate dedicated video just for this, these are bands, these are gaps. Bands are defined by having a lot of space for electrons to take up. Gaps do not. Now a typical conductive material would look like this, whilst an insulator would look like this. In the conductive material, if you add more electrons to it, you don't need all that much energy in order to squeeze them in. In the insulator, you need to jump the gap in order to squeeze them in, which requires a lot of energy. A fun side effect of that is that there are no true insulators and everything can be a conductive material if you just try hard enough. If you do actually get enough energy to jump this gap, then you can conduct electricity through anything, and I do mean anything. Then there are also semiconductors and doping them, but that's a topic for a dedicated video. So for now, let's just move on to ionic bonds. So, what are ionic bonds? Well, in order to understand that, we'll need to go all the way back to the beginning, the humble sigma bond. Now in this bond, I've been showcasing it between two identical atoms, most of the time like hydrogen or nitrogen, but you could actually have it between different atoms. And more interestingly, these atoms could have different electronegativities, and as such... sorry, it appears that in all that time I haven't actually mentioned electronegativity once. Whoops, so well, it just means how much any given atom attracts electrons. So high electronegativity fluorine is really good at taking the electrons away, whilst francium is really bad at it. Now back to the bond. What this effectively means is that if we have our sigma bond, then if one of these atoms is pulling more on the electron, then the bond shifts more towards that atom. It's honestly pretty simple stuff, but what we're interested in is the fact that this basically exists on a spectrum, from covalent through polar covalent up to ionic. So ionic, the name, comes from ions, so we know the charged atoms, and no, sorry, it appears that I haven't mentioned ions either. What kind of chemistry video is this? Well, ion is just a charged atom. Now with that in mind, we can take two of such ions, like chloride and sodium, and just smash them together. There we go, table salt. Or actually, not quite. You see, the reason why we differentiate between polar covalent and ionic is because ionic has a lot more to do with salts, crystals, solid state, whatever. The point is, it goes outside of the bounds of this video, and what stays in the bounds is extremely boring. So let's end this video with a bang, and something a tad more fun, and that is a particle sim. So, let's start by just creating a whole bunch of points. Okay, splendid. Great start. Now the rules I'll define for this will be simple. First of all, these points will have different charges, so either positive or negative. Negative charges repel each other, positive repel each other, and negative and positive attract. You know the drill. The point is, if I run the sim, we will get this. And the point I'm trying to make here with this particle simulation is that the reason why ions form crystals, the reason why ionic bonding works, is because that is just a natural way for ions to clump together. They just like clumping together. And if my physics sim was cleaner, you'd even be able to see the crystal structure. And speaking of the crystal structure, right about now there are actually two questions you could have. First of all, make it. Did you really spend almost an hour making a physics sim just for the sake of a single animation? Yes. But second question, more importantly, where do we go from here? Well, first we could branch off the covalent bonds and the carbons to go into organic chemistry, talking more in depth about carbon chains, electronegativity and the functional groups. From metallic bonds, we could talk about electricity, conductors, insulators, semiconductors, dumping, eventually making our way up to diodes and transistors. From ionic, we have the intermolecular interactions and even states of matter, slowly increasing in scale, explaining them all the way from quantum mechanics, or we could retrace our steps. That's because in the first episode of this series, I've started with orbitals, even though a more linear way to go would be to start the fundamental interactions and quarks. So in order to determine where we'll go with the series, I'll put it to a vote, and you can decide. But before we end this video, a quick word from the sponsor, and that is thickcoins.net. Have you ever looked at your nickels and thought to yourself, that's awfully thin? Well, Nickels got you covered. With their brand new and incredible formula, they managed to thicken up those coins real good. Just look at that thickness. You can use them for whatever you want. Self-defense, general prosperity, or just sheer enjoyment. Nickels for anything. But make it, I hear you ask. You don't even own a nickel. How can we trust you? Well, that is a fair question, and you'll be happy to know that this entire endorsement has been paid for by a single nickel. You see, I'm not all that famous as a person. I mean, don't get me wrong, 70,000 subscribers is really nice, but let's be real, it's not a golden jet kind of fame. Still, even despite that fact, I do get occasionally some requests for sponsorships, like 2 or 3 a week, I would say, from different companies of various sizes, asking me to either use their product in my videos or comically make an entire video about their product. And so far, I haven't accepted a single one. This is why this is the first sponsorship of the channel. I haven't accepted a single one of those requests, nor do I plan on do so. And that's because, you see, when you give me money for an endorsement, you are not paying for ad space. You are not, in fact, paying for airtime. No, what you are paying for is my words. And you cannot buy my opinions with money. My opinions will not change. If you want me to endorse what you do, you need to do something damn good. And that's why, when it comes to Theodore Nichols, he didn't send me an email. He didn't reach out to me. No, I reached out to him. And you wanna know why? It's because I believe in the nickel. And I don't need any fucking money in order to say that. Nickels, get them now, while you still can. Yeah, I don't care much for money. Apparently I'm like allergic to it or something. But I still, you know, need to pay the bills, the electricity for these lights, electricity for the animations I render. Something else was important. Food, right, food, shelter, these things are also, I guess, kind of important. So where do I get the money for them? Well, that would be my Patreon. So thank you all to all my Patreons for supporting me. That was not a joke, by the way. I did, in fact, turn down several sponsorship offers and instead reached out to Theodore Nichols myself so that I would get this one. So if you would like to do a cost-benefit analysis, this would be possibly one of the more expensive nickels ever sold. I regret nothing. I don't regret a single thing. It's gonna be great. I can't wait to get my thing. And you should get one too! But for now, that'll be it. Thank you so much for watching and have a great day. Bye!